Good to get started. All right, classwork for today is going to be these 6 examples. The overall skill set we've already addressed over the last couple days. Just some minor variations of some things we've already done. All right, so starting with the first one here, instructions are to write out the following sum. And we have the expression 2 to the k plus 1 times x to the k. We want to sum from 0 to 5. So we know we're going to get a total of 6 terms here. So to help keep track of where we are, we have k is equal to 0, k is equal to 1, k is equal to 2, 3, 4, and 5. So when we plug in a 0, we get 2 to the 0 plus 1, or 2 to the first, x to the 0. Plug in a 1, we get a 2 to the second, x to the first. Plug in a 2, we get 2 to the third, x squared. Plug in a 3, 2 to the fourth, x to the third. Plug in a 4, 2 to the fifth, x to the fourth. And then 2 to the sixth, x to the fifth. Oop, ran off the screen a little bit there. All right, x to the 0, that's just 1. So the first term is 2. And then that'll be 4x for the next term. 8x squared for the next one. 16x to the third. 32x to the fourth. And 64x to the fifth. So that is the expanded form of that sigma, or that summation notation. All right, good with 1? All right. Next 2, we're going in reverse. We are starting with something that's an expanded form, and we want to write it into sigma notation or summation notation. For this one here, I'm going to first concentrate on the coefficients. We have 3, 7, 11, 15, 19, 23. They go up by 4 each time. So we know it's an arithmetic sequence, so we can kind of treat those coefficients as like a 9-1, 9-4 problem to start off with. Let's just get an expression for those. If it goes up by 4 each time, it means 4 will be the coefficient of our variable. And then if we assume our counting with 1, which we can, it's our choice, then the term that follows would be, what would it be if we had 1 more in front there? Be a -1. So starting the counting with 1, 4n minus 1 will describe that pattern for the coefficients. All right, so now I'll dive into the summation notation. We already said we're going to start with 1 if we're going to use that expression. So that will be 4n minus 1 for the coefficient part. And now for the variable part, we have x to the first, x to the second, x to the third, x to the fourth. So if we begin our counting with 1, it's just x to the n. And it looks like if we use the exponent as our point of reference, the biggest value we have to plug in here, or the last value we have to plug in, will be a 6. Let's just check that with the coefficient part to make sure that still works. If we plug a 6 in here, 4 times 6 is 24. 24 minus 1 is 23. It checks with the last one. Let's double check that it worked with. We'll do, say, 3. We plug in a 3. That's going to be 12 minus 1 is 11. X to the third looks pretty good. All right, very often with these, rather than starting with a 1, very common to start with a 0. So what if we took what we already had and started it with a 0 instead of a 1? Well, if the 1 goes down to a 0, the 6 has to go down to a 5. And then these n's have to go in the other direction. So they have to go up by 1. So we know it's going to be an x to the n plus 1 here. And then we got to do potentially a little bit of scrap work here. So that n, if we're going to have it go up by 1, is going to be 4 times the n going up by 1 minus 1. Or it becomes the 4n plus 3. Now, the instructions did not specify what the lower bound had to be, so it's your call. There's no reason to have to do this twice unless there was some specific instructions that said that you had to do it twice, or you got this and it said it wanted that, or it's a small part of something bigger and you need to adjust them. Good with 2. All right, number 3. The bottom of the fraction, 2, 3, 4, 5, all the way up to 100. If we begin our counting with 1, that means the bottom of the fraction is 1 more than the number of the term. So we can begin, or make the bottom rather, n plus 1. Okay, up top, it's going to be x2, and then the pattern for the exponents, 3, 5, 7, 9, all the way up to 199. So we have an arithmetic sequence for the exponents. The exponents are going up by 2 each time. So we make 2 the coefficient of the n. And then if there was one more term in front, it would have to be a 1. So 2n plus 1 looks like it should work. So if we test it plugging in a 1, that would make the first term x to the third over 2. That seems to work. We are going to have the upper bound, the biggest number we plug in has to produce 100 on the bottom. So I'm thinking that should be a 99, and we'll just double check that with the exponent. If we plug in a 99 here, does it give us 199 back again? Well, 2 times 99 is 198, plus 1 is 199. And then the last thing we have to concern ourselves with is we have alternating signs. We're going back and forth between positive and negative signs. So we're going to have a -1 to some kind of power going on in here to make it alternate signs. It's a little bit of a guess and check typically with these, depending on what the sign pattern is and what you begin with, depends on what you need that exponent to be. So what if we made it just a plain n? If you plug in the first value, -1 to the first is -1, that would cause the first term to be negative. We want the first term to be positive. So that means we want to adjust that typically by an n plus 1 or n minus 1. Sometimes it doesn't matter which one you pick. I'm going to try an n plus 1 and see what happens. So if we plug in a 1 here for the very first value, that makes it -1 to an even power, which would be positive. Then if we plug in a 2, which would be the second value, that's -1 to an odd power, which would be negative. So that should work. Normally, you don't see the -1 this as the second part. Usually they put it in the front. So I'll write that so it looks more like what you would typically see. +1. That's a little sloppy. That's a plus. And as we've talked about, typically there are multiple ways that this could be written in order to produce that same sequence. That would be one of the more straightforward ways to get one. And if you needed to, again, if you wanted to start with 0, you could adjust all those things in there. But I think we've seen enough of those examples. Good with 3? All right, number 4. Find the coefficient of x to the 4th in this summation notation. All right, so if we were to write out this whole thing from 0 to 8, that would be a total of 9 terms. So one thing you could do is write out all 9 terms of this expansion, identify where the x to the 4th term is, and then I see what number is in front of it. And for this particular problem, there's nothing really wrong with that, but we don't have to do that much work. The only way that we're going to get an x to the 4th is when we plug in a 4 for k. So if we have to plug in a 4 for k, there, it means we have to plug in a 4 for k there. So 2 times 4 is 8. 8 plus 5 is 13. The coefficient in front of the x to the 4th must be a 13. Now, if you're not comfortable with that thinking, or you're not quite sure if that's right, you can always just start the pattern and verify, yeah, that's true. So if we plug in a 0, 2 times 0 is 0. 0 plus 5 is 5, x to the 0. Then plug in a 1. That'll be 2 plus 5 is 7, x to the 1st. Plug in a 2. That'll be 4 plus 5 is 9, x to the 2nd. And at this stage here, you probably see enough of this where you can extend that out. 5, 7, 9, 11, x to the 3rd, 13, x to the 4th. And there you go. That confirms that 13 must be the coefficient. All right, a slight level up from number 5. Same type of question, but instead of asking us for the coefficient of x to the 4th, they're asking us for a coefficient of x to the 7th. So I'm going to stick to a shortcut here. The only way we're going to get an x to the 7th if his k is 5. So what I'm going to do is plug the 5 in here, and that will give me from this part what the coefficient of x to the 7th is. So 3 times 5 is 15, and then 15 minus 1 is 14. And again, if you're not overly comfortable with that, or you're not confident with the way you mental math to get there, you could always expand it out either all the way till you hit the 7th, or enough to establish the pattern and extend the pattern from there. Good with 5? All right, one more problem for today. This one's reasonably challenging. We got some more stuff going on. So we have this summation notation here, and then that is being multiplied by this binomial. So mental mathing where an x to the 3rd is going to be, or what gives us an x to the 3rd, that's tough stuff right there. I think that's probably a little bit more than most students are able to do. So here's what I'm going to do. I'm going to leave this 3 plus x in front, that binomial, alone for now. And I'm going to expand this out enough to identify the pattern. So it's 3 plus x times that polynomial we get when that gets expanded out. So when we plug in a 0, that's going to be 0 plus 3 is 3, x to the 0. Then we plug in a 1, so that will be 4 plus 3 is 7, x to the 1st. Plug in a 2, so that will be 8 plus 3 is 11, x squared. Plug in a 3, that will be 12, 15, x to the 3rd. And at this stage, you should feel pretty confident of what the pattern is for this polynomial. So 3, 7, 11, 15. So 19, x to the 4th. And then 23, x to the 5th. Blah, 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 blah. That's more than enough to establish what we need. All right, so now what we have to do is this binomial times that infinite polynomial. Not actually infinite. For what we're doing, I guess we can consider 100 infinite. It's not like we're going to write all that out. So 3 times everything, x times everything. And I will make that first term just a plain old 3 to make this multiplication a little bit easier. So we're going to multiply 3 times 3 is 9. 3 times 7x, 21x. 3 times 11, 33, x squared. 3 times 15, 45, x to the 3rd. 3 times 19, I think that's 57, x to the 4th. 3 times 23, 69, x to the 5th, blah, 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 blah. So that's 3 times everything. Now we have to do x times everything. So x times 3 is 3x. and I'll write it so it's underneath, so it's easy to combine the like terms. X times 7x, 7x squared. X times 11x squared, 11x to the third. X times 15x to the third, 15x to the fourth, and we don't need to go any further. Dot, 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 dot. Then all the stuff from the first round of multiplication adds up with all the stuff from the second round of the multiplication, and the only thing we care about is that right there. That's what's going to give us our x to the third power. We have stuff in the front. We got a whole lot of stuff that follows, but that's the only one we care about. So the coefficient for that is 56. Guys okay with that? That 15? Oh, because that was, I guess I kind of wrote that too close. Because it's 3 times this gives us this line. And then x times that gives us that line. No problem. You good? All right.